Okay. So I posed a question. If we're at the Earth and want to just fire a projectile from the Earth to the orbit of the moon, not to put it in orbit, in that orbit, just to get it there. Okay, so maybe the moon will come along and capture it or something. Question is, if we neglect the atmosphere, which of course can't be neglected, if we want to really do this, and it's really not practical to do it. I'm not sure we even have the materials that would allow us to fire an explosive projectile. You know, cannons tend to blow up. In the early days, decades of developments of cannons, they killed more operators than they did enemies. You know, it's a real science and art to build a cannon that'll hold together and not kill the people that are operating it. So a cannon that would fire something at that speed, you know, I don't think it could be built, but I'm no material scientist and I haven't tried to analyze it. All right. A rail gun maybe, but there are problems with that too. You have to be pretty low. So I mentioned there are two conservation laws that we really have to think in terms of. One being conservation of angular momentum, the other being conservation of energy. Well, angular momentum, if we shoot straight away from the Earth, we have zero angular momentum relative to the center of the Earth, which is where we see gravity originates. Okay, the point at which gravity, the gravitational pull pulls. So angular momentum isn't going to be particularly informative, but conservation of energy is. Now, at this stage, 2 weeks before finals week starts, we're having a little bit of trouble even stating the law of conservation of energy, okay? Even though we've been through those chapters, done those problems and stuff. So, you know, I'm not saying that you're deficient or anything. Well, that is seriously a deficiency. It's just that maybe you're a little focused on the trees and not seeing the forest. And it's a lot easier to figure out how to solve a challenging problem if you do both. Okay, so we want to step back and review where the trees are. So we first have the work kinetic energy theorem. Okay, how's that derived? Well, we can derive it by integration, and you should know how to do that. I could put that on the final. But we can also derive it just using the equations of uniformly accelerated motion, which is just equivalent to using an integral of a constant. Okay, and you have the equation. It says VF squared equals V naught squared plus 2A double delta X or delta S, whatever. Okay. And net force is, acceleration is net force over mass. So you plug that in for the acceleration and rearrange the equation and you get this. Now make sure you know how to do that because there's a very good possibility that I'll ask you to do that either for energy conservation or impulse momentum. Okay. And for impulse momentum, it's even simpler. You get final velocity equals initial velocity plus acceleration times the time interval. Acceleration is still net force over m, and you get the basic statement for constant force of impulse momentum. And the definition of momentum and the definition of kinetic energy come out of those developments. If you don't know that, you're at risk, number one, of not being able to answer a question about where they come from. And number two, you don't have an integrated understanding of first semester physics, which you're going to need for the final. Okay. So make sure you have that down. Now, that work is equal to change in kinetic energy. That work comes down to work done by the conservative force, work done by the non-conservative force. Okay? And the work done by conservative force is equal and opposite to what we call potential energy. Okay? And of course, people never seem to know, no matter how many times I state it and use it in examples, that our definition of potential energy is that it's equal and opposite to the work done by the conservative force. Meaning, if you do an integral for the work done by the conservative force, like the integral from 0 to infinity of negative g big M little m over r squared, you know, usually the energy relative to infinity. We need to understand that. So try to get that into your head and apply it to these problems. So far I've got my non-conservative forces into this formulation. In the example we're talking about, we remove air, which essentially removes all non-conservative forces. Okay. And we'll simplify it by removing the work done on this shell by the sun and Jupiter and the asteroids and the rest of the galaxy and the rest of the universe, and just concentrate on the work done by the gravitational field of the Earth, which makes it a very simple problem once you have the concept down. So we have this. The only forces are conservative, then change in kinetic energy and change in potential energy are equal and opposite. Their sum is 0. It's the same thing as saying they're equal and opposite. If you don't understand that statement, ponder it until you do. It won't take you long. Okay? And you probably understand it already, but make sure you understand it. You're missing something if you don't. Okay. Well, now we're going to go from the Earth to the moon. What's the change in potential energy from the Earth to the moon? Well, I kind of messed this up when I did it the first time. I got the limits in the integral backwards or something. But here we got the Earth, mass big M. And here we got really far essentially an infinite distance from the source of gravity. Okay? It's not necessarily the Earth, it's just something with mass big M. And this is really, really far. Or if you just kind of flick it with your fingernail, it'll never come back. The force is so tiny out here that it'll never slow down to 0. Okay? For practical purposes, if you've got a magnet over there 20 feet away from me, you're not going to affect the metallic pin in my shoulder. Okay? You're not going to affect this steel ball. You're not even going to affect this magnet in any way we can measure with any instrument in this lab. With a really sensitive balance, yeah, you could detect the difference, but the magnetic field basically when you get a little ways away from the magnet, it falls off as a cube of the distance. Okay, so if at even 20 centimeters, you got a Newton of force. Okay, at 20 feet, you're going to have 1/30,000 for that. Okay, ballpark. I think that's probably accurate. And that's a 30,000th of a Newton. You know, if you eliminate all other forces, that'd be measurable. But again, I don't think we have any instruments here that would directly measure that. Oh, that was my mass. Okay, so now what we want to do is we want to see how much work gravity does as we move from here to here. Okay. So we take this interval, we take a typical increment at distance r star. That's our sample distance within this interval. This should be familiar to you from the way you developed integrals in calculus a year ago. Okay. A little more than a year ago. Okay, so the force of gravity negative big G big M little m over r star squared. The work done by gravity, I'll use a delta here. It's probably not standard, but I like it. The contribution up to the work done by the total force. And we're going to call this the ith interval. I'm not going to put an I on the R I did before, but you should know how to do that. And if you don't, you should review your calculus. Okay. I don't have time to do that again. I mean, I have time. You don't have time for me to take the time because you got stuff to do to get you ready for the final. Okay. So, well, the W sub I is what? It's negative big G, big M, little m, over R star squared delta R. Now we'd have an R sub I squared and a delta R sub I for the delta W sub I. Okay. So I'll actually put an I on this and an I on this. Take long. It wasn't there here, but it's there here. It's here, there. I don't know what it is. Okay. Makes sense? That's the work done. It's work done by gravity between here and there. Okay. Why is it negative? It's because gravity is in this direction and delta R is presumably a positive increment as we're moving along this path from here to here. That's implicit. I haven't stated it, except I just did. I don't have it on the board. And this implies that the total work which is the sum of these W sub i's, approaches the integral of negative big G, big M, little m over R squared dr. Okay. And that would be the integral from here to there, from here to there. You can worry about what the limits would be. If we're going from the surface of the earth, then we go from the radius of the earth out because we're not going to launch that projectile from inside the earth. Unless we've got a big, well-constructed tunnel to protect everybody from the blast of the shell. Okay? Explosion that projects the shell or whatever it does. Maybe we may think of a great big spring. I don't think that's practical. I think the spring would fall apart long before anything good happened. Okay, so and there we have it. And that integral would be from the initial distance from the center of the planet, which I'll call R naught, to infinity. Now, actually, it'd be from 0 to whatever R you want to call this, R big, okay? And then you're gonna do a limit as R big goes to infinity. That's how you do the proper integral, as you recall, and you should recall. Okay? Now, the work done by gravity as we move away from here is positive or negative. I'm sorry, the change in potential energy. It's a change in potential energy, positive or negative. But well, you do this integral. And you get big G, big M, little m over R squared. Okay. Sorry, you get negative big G, big M, little m over R squared. But you get a negative when you integrate R squared, and you get a negative because this is your lower limit. Upper limit minus lower limit, right? So you get two negatives on something that's already negative, which makes it negative. And that's the thing I kind of didn't say right when I did it. And I got to thinking about orientations and stuff like that and didn't quite write it out correctly. Okay, it just wasn't being very careful. I wasn't being very specific about how the integral was set up, and that led me to write down something wrong. But there it is. Well, and it's not over R squared, it's over R. So the gravitational potential energy relative to starting point here as you go out here is going to be positive as you move away, right? Okay, because as R gets bigger, your potential energy measured from here gets smaller. The magnitude of the potential energy gets smaller, but the potential energy is negative. Okay, so smaller negative is bigger than a bigger negative. Okay, or greater than a bigger negative. That's not particularly important because this is not the way we calculate gravitational potential energy. This is the way we calculate gravitational potential energy if we want to get confused, which we probably are at this point. The way we calculate it is to go from here to here, so gravity is doing positive work. Okay. Now, this will be the work done by gravity relative to R naught. Okay. If you want to do the work done by gravity relative to infinite separation, you reverse the integral. You go from infinity to R. And in this case, you're moving in the direction of gravity, so it's a positive integral, okay? And this is this. Something's wrong with that. Every time I try to explain why we integrate from infinity, I get screwed up. Hang on. This being too stupidly intuitive. It's integral negative big G big M little m over R. dr is negative, and so is the force of gravity. So this product is positive. And of course, then this is what we get. And we get this. And as is obvious, if you understand that the gravity and the displacement are in the same direction, you have to get a positive result. It could not have been negative. I just didn't want to put the negative in front of that because, again, we look stupid. Okay. So, but now back to where we are. Okay. Here's the whole development. I haven't written it down. Actually, I have implicitly here when I said the work done by the conservative force is equal and opposite to the change in potential energy. But I'm going to say it real explicitly. That it's equal and opposite to the work done by the conservative force, which then equals negative big G, big M, little m over R, which is a formula you probably memorized, at least long enough to do your homework so you could forget it before you had to do it again. But don't forget it, okay? And don't forget where it comes from. Just write down this integral correctly, as I didn't. And it comes right up. And if you just can't bring yourself to write the integral correctly, write it incorrectly and put the proper sign on it at the end. Okay. You know the gravity is doing positive work as you move toward the planet. You know that the change of potential energy is equal and opposite to the work done by that conservative force. Therefore, you have this. Okay. That's a little r. Probably should have been a little r, but again, I didn't want to mess with dummy variables, so I used a big R for my limit. But this is otherwise identical to the formula you see in your text. And then what did we do? You work out centripetal force equals gravitational force. And you get the velocity you need at distance r, which gives you the kinetic energy at distance r, which is exactly half the magnitude of the potential energy. Kinetic energy is positive. Half the magnitude of this negative potential energy gives you a negative 1/2 big G big M little m over R, and that's the total energy of a satellite. Now that's not relevant to the simpler question that I asked you originally. Okay, the simple question I asked you originally was how fast it'd have to go to get to the moon. Okay, well, now you can answer it, and I'm going to answer it pretty briefly. And we put together the details we need to. We spent enough time on this. It's partly due to my error. I don't know what it was. Call it what you wish. So the words are kind of running together there. Earth to moon, no air, direct shot. Well, let's change potential energy. This will be the radius of the moon orbit. Going to be negative big G big M little m over radius of the moon orbit. Minus this, and it'll be minus negative this, because of course potential energy is negative potential energy from infinity to a point is this. And that is what we call your potential energy at the point. Now, is this going to be a positive quantity or negative quantity? Now, radius of the Earth is less than the radius of the moon, right? Okay. So which of these is going to have the greater magnitude? Just say less or greater. This one get less or greater? Okay, I'm seeing a couple of votes for greater. Okay, yeah, the magnitude of this quantity is greater than the magnitude of this quantity because this denominator is less. Okay, denominator here is greater. So numerically, the absolute value of this quantity is greater than the absolute value of this quantity. Of course, this quantity is positive in this case. Abbreviate moon orbit. This positive quantity is greater in absolute value than this negative quantity. Okay, negative quantity is actually pretty small. Okay, so that if your kinetic energy, when you get out to the orbit of the moon, is zero, and that's exactly what it has to be if you're just going to barely get there, right? Gets to the orbit of the moon, velocity is zero. Of course, now it starts to fall back. And your change in kinetic energy has to be equal and opposite to your change in potential energy, which means that your initial kinetic energy minus your final kinetic energy is equal to the negative of your potential energy change. Final kinetic energy is zero. Learn what you see me do to do things carefully. The change in kinetic energy is not the initial minus the final, it's the final minus the initial. Okay, so you get this negative is equal to the negative of this potential energy, which is going to be negative big G big M little m over radius of the Earth plus big G big M little m over the radius of the moon orbit. Now, it's conceptually very simple. You get the problem and you say, okay, there's no dissipative force because we remove the air. So we have to have enough kinetic energy to overcome the potential energy change. At that point, you have a couple of options. One option is to use this formula. And when I put a delta on that, that is a change of potential energy from infinity to here, but we take this to be the potential energy at this distance. Okay, meaning we're doing the potential energy relative to infinity. I shouldn't have had a delta on that. It is a delta PE from infinity to here, but that's a definition of the work or the definition of the potential energy relative to infinity. So it's the potential energy. So again, change in potential energy is just a change in this quantity, big G, big M, little m, negative big G, big M, little m over R. Do that, there you have it. So again, you see the problem, the quickest way to conceptualize it is potential energy is going to increase. I know that because gravity's pulling back. When we're talking about gravitational potential energy, we usually want to do it relative to infinity. So if you do it relative to infinity, and here are our expressions. Using those expressions, we get this, and if you got the numbers, it's easy. If you don't have the numbers, well, you just multiply all this by 2 over little m, and little m goes away, and you got a 2 in each denominator. And that's your expression. And you can plug that in for any two distances. Okay. This is the potential energy at the moon's orbit. Okay, we accept what I just developed. Okay. If we're going from here to there, we take the potential energy there and subtract off the potential energy here. If I'm going from mile 17 or 14, 15, whatever, right down there, to mile 30, then we subtract 15 from 30. So this is like our 30. That's our potential energy at the moon orbit. It's negative, and this is confusing. It's negative, but it's a smaller negative than this is because this R is less than this R. Okay, so that's all the point of confusion. I remember, being a little confused by that. Matter of fact, a lot confused for a lot when I first learned this. It's a freshman. We're subtracting the potential energy at the Earth, which is this, and it's subtracted from the potential energy at the moon. Just like we're driving from mile 15 to mile 30, except maybe we're driving from mile negative 30 to mile negative 15. They're both negative. From negative 30 to negative 15 is still 15, right? Okay, so we're gone from a negative number that's closer to 0 to a negative number that's further from 0. Okay. Of course, that would be negative. So what I just said didn't make any sense. Let's make sure it makes sense. Pause for a second. Okay, so what I said up here is we're going from RE to R moon. Okay, and I said it backwards there. We're going from the negative number that's further from 0 to the negative number that's closer to 0, and it's positive. Just like going from negative 30 to negative 15. I just had those in wrong order, and that was maybe unforgivable, so be it. Now, your question was down here and on the signs, because these signs are the opposite of these signs. Why? Because the change in kinetic energy is the negative change in potential energy. So the negative change in potential energy is going to change these signs. So those signs are correct because this is the negative of the potential energy change. The kinetic energy change, which I wrote down backwards carelessly, final minus initial, right? And the final is zero. So as before, I should have a zero here. So we get negative initial kinetic energy, which is negative 1/2 mv, and I squared is the negative of what we have up here. Okay. And now you have a negative equal to a negative quantity. This being a negative quantity because the magnitude of this with denominator RE is greater than the magnitude of this with denominator R moon orbit. Okay. That halfway makes sense? Sort it out. Do a better job of it than I did. Okay, good question. This came up about Lagrange point. And it's the point where for example, I use the example of the Webb telescope. It's a Lagrange point between the Earth and the Sun. The point where the gravitational pull of the Earth is equal and opposite to that of the Sun. So the thing is much easier to keep in a very stable orbit around the Sun. Okay, you can have one between the Earth and the Moon. Okay, so let's just do the Earth and the Moon because that was what the question was about. Your gravitational field of the Earth at distance r sub L is just this. Okay, and for the Moon, well, how close are you to the Moon? If you're at r sub L from the Earth, you're at radius of the Moon orbit minus r sub L from the Moon. So right there's the gravitational field of the Moon when you're distance r sub L from the Earth. Again, if you're distance r sub L from the Earth, your distance radius of the Moon orbit minus r sub L from the Moon. Make sense? And you do all picture. Here's the Earth, here's the Moon, and here's your point. This is r sub L. This is the radius of the Moon orbit. And this is radius of the Moon orbit minus r sub L. Okay. Yeah, it's an easy equation, so I'll just expand the denominator, multiply through by common denominator, and you got a quadratic. Now notice that this is the velocity you need if you didn't have air resistance. You do have air resistance, so you have a non-conservative force. So that the kinetic energy plus change in kinetic plus change in potential has to equal the work done by the non-conservative force. Now you still put the negative change in potential energy over here, which is going to be this, but you have the non-conservative force here, which is added to it. The work done against the air, let's say, will be added to this. You're going to need more velocity. Okay. And the reason you're going to have more velocity is you're adding this to a negative quantity. Well, think it through, because what I'm about to say probably doesn't make sense, but work it out. Okay, now quick synopsis. We had a lot of questions, some interesting stuff. Okay, so it was good to talk about. You got to get into elasticity. Now you still have the assignment to do tomorrow is the last assignment on rotation. For sure, that's right. And then you have one or two assignments, and early next week we kind of wrap up the assignments. Okay, so we can do some review. And this is on simple harmonic motion. Ideal springs. F net equals negative kx. So mass times acceleration equals negative kx. So acceleration equals negative k over mx. Acceleration being the second derivative of position. And you know differential equations, so you know then that x equals a cosine of omega t plus phi. Phi is an arbitrary constant. Omega is a square root of k over m. Or b cosine of omega t plus big C sine of omega t. You've got angle formulas that allow you to convert this form to this form. Okay. So that's it. Now you know the equations of motion. That's the equation of motion. Okay. It's all consistent with the stuff that we've done with energy. This is the motion. Now, of course, you've got two more equations. Take the derivative of either one of these, and you have the velocity. Take the derivative of either one of these, and you have the acceleration function. Okay. One more thing. You have the unit circle model. Here's phi. That's the angle on the unit circle at which you start. And then you move angular velocity, square root of k over m. You've got some radius, which we'll call a. And at time t, you will have moved through angle delta theta. You relabel my a here, so I've got my, here's your delta theta angle here. Your radius of the circle is a. I put that out here. Okay, so theta equals omega t plus phi, and x equals cosine theta. It's by the unit circle model. Just totally understand that, as well as the fact that if you want a vector out here, then this vector could be your velocity. Which is just omega times the radius. There's your velocity. This is a vector that has components. One of the components is the x velocity. The other component would be the y velocity of this point as it moves around the circle. Not only that, but you have an acceleration, a centripetal acceleration, which is a vector. And it has a component in the x direction that's equal to the acceleration, the actual acceleration of the particle. So that model is really important. I'll explain it in detail next time. I want you to get the idea that this is central. And then all the stuff you know about energy. Okay, so that what's a potential energy at position x? Now position x is with respect to an equilibrium position, right? It's always 1/2 kx squared. Total energy is 1/2 Ka squared, because the maximum potential energy occurs when the thing comes to rest at distance a from the equilibrium point. So there's your total energy. But your total energy is just your kinetic energy, 1/2 mv squared plus 1/2 kx squared, the potential energy that you get just by integrating this. Integral negative kx is negative 1/2 kx squared, right? So this expression is your conservation of energy for an ideal pendulum, for an ideal simple harmonic oscillator. Could be a pendulum, could be a mass on a spring. For pendulum, if the mass of the pendulum is out here, and you're at a small angular displacement, A is going to equal, so you got mg here. This component is going to be mg times x over L. This component of the tension, again, I'll explain this in detail, but it's as simple as this whole picture. I've almost got the whole thing here, so give me another minute to finish it up. So K is going to be mg over L. A pendulum behaves like a simple harmonic oscillator with force constant mg over L, where L is the length of the pendulum. Okay. It is simple trigonometry. And this is for a pendulum that doesn't go too far from equilibrium. Pendulum doesn't go too far from equilibrium. The tension is almost equal to the weight. It's not quite equal to the weight. You do have the tools to deal with the differential equation that does it accurately, but this is a pretty accurate approximation. So pendulum of small amplitude, right there is your set of relationships. This gives you velocity in terms of position. If you know the position and the amplitude and K and the mass, you find the velocity at any position. The only one unknown remains. You can, of course, put these equations together to derive this. Okay. Go back. Well, never mind. So that's kind of what we're doing. You really ought to read that chapter, because we've only got, 2 weeks, and it's going to be finals, first day of finals. Okay. Then we might have some time to review things and try to put some more things together.